We talked about energy, momentum, then collisions, conservation laws, invariant quantities like E square minus P square C square, and these are quite helpful in solving various problems in dynamics. Now, the very basic equation in dynamics, when we start our Newtonian mechanics early school days, the basic equation that governs the entire thing is F equal to m a. So, that equation, let us see how this is replaced in special relativity. This equation tells me several things. One is the acceleration, which is the rate of change of velocity, is in the direction of applied force. This is a vector equation. So, this acceleration, which is dv dt, and hence in a small time interval the change in velocity dv, this change in velocity must be in the direction of the applied force. And this we had used very extensively in our school days, that if there is a force in x direction, there is no effect of this force on the motion in y direction. When you do projectile problem, then you say that the force is in vertically downward direction. So, if you have a projectile, you just throw a particle at some angle with the horizontal near the earth's surface, and then it goes in a parabolic path, and you say that everywhere the force is in downward direction, and that is mg. Everywhere the force is mg, and that is in downward direction, and therefore, in x direction there is no acceleration. In x direction, whatever is the initial velocity, that initial velocity will remain there everywhere in this path in x direction, because the force is in y direction, does not have any effect in the x direction. So, this we had been using very regularly. So, and that comes from this particular equation. Then this acceleration is just given by this force divided by mass. Mass is of course mass, and therefore, if you have a say constant force in a fixed direction, and if the motion starts in that direction only, the speed will keep on increasing. Speed will keep on increasing. We know all those equations. V is equal to u plus at, and this a is f by m into t. So, as time passes, this velocity keeps on increasing beyond any limit. These are regular Newtonian mechanics equations. Now, once we are in relativistic regions, these things will not work, that we know. Mechanics, the rules of mechanics, the rules of given by Newton's laws, these law, this is not invariant under Lorentz transformation, and in experiments also we see deviation from Newton's law. So, the real laws of motion are somewhat different from this, which are describing the experiments nicely, and which are invariant under Lorentz transformation. So, we have seen that we write this as f is equal to dp dt. This is okay. This is okay in relativistic regions also. The only thing is this p is no more mv. If I write m naught, let us say v by square root 1 minus v square by c square. We call it rest mass. I repeat once again, we call it rest mass. We put an extra symbol here, m naught, but I do not give much importance to the so called relativistic mass. This is just the mass, and the relativistic mass in this lecture itself you will see that it is not very significant quantity. If you think that if I replace this mass in Newton's law by relativistic mass, that will not work. In the linear momentum definition, yes. In the linear momentum definition, if you replace mass by this so called relativistic mass, the linear momentum is given by this. But beyond that, you cannot stretch the application of the relativistic mass. So, just look at this dp dt. dp dt, let me write it m naught v gamma. So, dp dt, if you write, this is m naught gamma times dv dt and plus v times d gamma dt. Okay. Just differentiation of these quantities, product of two quantities, both depend on v and v depends on time, and therefore, you have that product rule which tells gamma dv dt plus v d gamma dt, that is the differentiation, that is dp dt. Now, this d gamma dt is somewhat typical. You can do that, of course. This is d dt of 1 by square root of 1 minus v square by c square. You can do this algebra. This will be minus half and then 3 by 2 power of this, and then you will have minus 2v minus 2v and then dv dt by c square, so on, and you can make simplifications, put there and do all those things. But there is another way to do it which is algebraically simpler. That is, if you look at the total energy is what? Total energy is m naught c square gamma, and therefore, d gamma dt, if you have to write, if you can get this de dt, you will be done. So, let us try this de dt. This de dt will be m naught c square d gamma dt. And what is E? What is E? E is m naught c square plus kinetic energy. So, it is d dt of this. And since this is constant, m naught c square is constant for a particle, we are talking of one particle. So, it is dk dt, it is dk dt. And what is dk? Dk is f dot dr, right. Change in kinetic energy. We started from here. If you have a particle, if a force acts on it, there is a displacement, there is a work done by the force, and that work done gives you the change in kinetic energy. So, dk is f dot dr dt, and hence you can write this equation as this equation, or from here you can write d gamma dt is equal to 1 by m naught c square, 1 by m naught c square, and then de dt, and de dt is, and this you can write f dot v, this you can write f dot v, this one dr dt is v. So, f dot v, this is f dot v. So, f vector dot v vector, this is d gamma dt, and that d gamma dt let us write here. What do you get? dp dt equal to, and which is force. So, force is equal to dp dt, and dp dt is m naught, let me open it, m naught gamma dv dt. So, I have written this term m naught gamma dv dt, I have written plus m naught v here. So, m naught v here, and then you have d gamma dt, and d gamma dt we have written here f dot v divided by m naught c square. So, this is, from here you can write dv dt. So, your dv dt is this minus this. First let me write that f minus m, this m naught you can cancel. So, f and then you have f dot v here, this is a scalar quantity, then this v here, and divided by that c square here. So, it is this part. So, this is f and minus f dot v, v here by c square here, and this whole thing, and then 1 by m naught gamma. Okay. So, that is dv dt. So, you have two terms, dv dt is equal to, first term is f divided by m naught gamma, this is the first term, and then you have another term which is minus f dot v, then v, and then m naught c square gamma. Okay. So, this is how acceleration is related to the force. In Newton's law, it was a very simple relation, acceleration is force divided by mass, and if you still have attachment with relativistic mass, this is that relativistic mass m naught gamma. So, Newton's law will be like this, dv dt is equal to force divided by, let us say, relativistic mass, but it is no use, because putting that relativistic mass in Newton's law, it does not give me the right equation. So, if I have this equation, f is equal to m dv dt, dv dt is equal to f by m, and I say that no, it is relativity, do not use rest mass, use relativistic mass, you will get only one term, and therefore it does not help, and that is why we say that relativistic mass is not a great quantity. Now, if you look at this equation, first thing is that dv dt, the acceleration, also has a term which is in the direction of the velocity. Force need not be always in the direction of velocity. In the projectile case also, you know, force is always in vertical direction, vertically downward direction, but the velocity is very different. In this picture, nowhere the velocity is in vertical direction. So, f and v are not parallel to each other. In Newtonian mechanics, f and a are parallel to each other. So, if you have v here and you have dv dt here, that means acceleration is not necessarily in the direction of force, because this v may not be in the direction of force. So, you do have a component, and from here also you can get a component, but not necessarily. So, the first thing we learn is that acceleration is not in the direction in general. So, our experience that if I have a force in x direction, it will not affect motion in y direction or z direction or anywhere in yz plane, that notion has to go away. The acceleration can have a component which is not in the direction of the force. There are some special cases where acceleration is indeed parallel to the force, and let us see what these are. So, first case I consider when the force is in the direction of velocity. So, if the force is in the direction of velocity, for example, if you take a particle which is at rest and then apply force, so what will happen? So, here the force will generate the velocity, and starting initial velocity will be 0, and therefore, this term will be 0, and so the dv will be in the direction of f, and hence you will have velocity produced in the direction of f, and all the time that will be like that. First v was 0, and after that you will have something else, but then let us see what happens. So, if force is parallel to the velocity, then your dv dt is given by f over m gamma, m naught gamma, and minus this is f into v. F is parallel to velocity. So, this f dot v is just f into v, and then this is v. So, if I take everything in one direction, this will be f into v square. Okay. So, let us take that direction as the x axis direction. All right. So, in that direction, if I write only the magnitudes, because all directions are same, force, velocity, everything, all directions are same. This force, this velocity, and then from there this dv dt, all directions are same. So, I am dropping that arrow sign on the top, and therefore, I can write dv dt is equal to f over m naught gamma. Look at here, look at here. And then you have f by, so the first term is this, and the second term is minus f into v, cos theta is 1 into v. So, f into v square. So, f into v square and divided by m naught c square gamma. So, if you take f divided by m naught gamma common, f divided by f naught gamma take common, then this is 1 here, and f divided by m naught gamma you have taken common. So, it is minus v square by c square. So, it is this, and you can write this as f divided by m naught gamma cube. Remember, gamma is nothing but 1 by square root of 1 minus v square by c square. So, or you can write this as f over m naught and then 1 minus v square by c square to the power 3 by 2. So, dv dt is given by this. If you want to say that okay, it is still in the form of force divided by mass, then your mass is this much, your mass is m naught divided by 1 minus v square by c square to the power 3 by 2. So, for the cases where the velocity is in the direction of force, you have this kind of mass. If you want to define another mass, it is like this. And the other case is when f is perpendicular to the velocity. If force is perpendicular to the velocity, in that case this f dot v will be 0, and then the equation will be just dv dt. dv dt is equal to f divided by m naught gamma. So, if you want to define mass from f equal to ma, your mass will be different for velocities parallel to the force and velocities perpendicular to the force. So, no sense. So, best thing is that just mass means mass, rest mass, that is all, and after that the form of equations, expressions, they are different. Now, let me solve a problem before I close, and the problem is very simple, is just a particle at rest on which a force, constant force is acting. So, a force, a constant force f I cap, let us say f naught I cap, acts on a particle of mass m naught. So, I am gradually dropping that idea of rest mass, everything is rest mass and nothing else. So, a constant force f I cap acts on a particle of mass m naught at t equal to 0. The particle is at the origin and has 0 velocity and at rest. So, you have to find the velocity or speed find the velocity of the particle as a function of time. One of the simplest problem. So, you have a particle of mass m naught at time t equal to 0, it is at rest at origin, and then a force acts, and then the force remains constant, this f naught I in the x direction. So, the force is in this direction. Now, as I said, since it is at rest to begin with, your dv dt is given by this. So, dv is in I cap direction because f is in I cap direction. So, the velocity which is produced is in I cap direction, x direction, and after that there is no chance of getting any y component or z component, because once it is, this is in the direction, the velocity is in the direction of force, this velocity is in the direction of force, is the same direction, and once again the same thing will happen, and therefore motion is only in the x direction. So, acceleration is in the direction of force. So, I wrote here acceleration is not in the direction of force, but this is in general. There are cases in which it is, and in our case it is parallel to the velocity, force is here, force is parallel to the velocity. So, we will be using this equation to get the velocity. So, I have dv dt, since everything is in x direction I can drop this arrow sign here, is given by f divided by m naught 1 minus v square by c square and then to the power 3 by 2. And from here you can obtain velocity as a function of time and all that, but I will be doing a simpler route, and that is, let me write f as dp dt, and since everything is in x direction, f is just dp dt, everything is in x direction, and this f is constant, f naught, this f is constant, this is f naught, and therefore dp is just f naught dt, and hence p is f naught times t. Initially at t equal to 0, velocity is 0, and therefore the linear momentum is also 0, and hence that integration constant is 0 and p is f naught t. And what is p? P is m v m naught v square root 1 minus v square by c square, this is p, this is equal to f naught t, and hence you can write m naught square v square is equal to f naught square t square and multiplied by 1 minus v square by c square. Okay, square both sides and take this to the other side. So, you have f naught square t square multiplied by this is this. Collect the v square term together. So, you have m naught square here, v square plus f naught square t square v square by c square. So, I have taken this term minus v square by c square multiplied by this, I have taken it here, that is f naught square t square. So, you can take v square common and divide on the other side. So, v square is equal to f naught square t square and then divided by m naught square from here plus f naught square from here, t square from here divided by c square. Okay. So, I have taken v square common, and then in the bracket I will have this m naught square plus f naught square t square by c square, which will go on this side, and that will be v square. So, what is v? V is equal to f naught t divided by square root of m naught square plus f naught square t square divided by c square, square root of this, it is like this. Let me multiply both sides, numerator and denominator, by c. So, c here and c square. So, this will become just this one, and this will be multiplied by c square. So, m naught square c square plus f naught square t square. It is like this. So, you can see that if I take this f naught t here and then f naught square t square here, compare this. So, this denominator is greater than this f naught t, square root of this quantity, the denominator, this entire denominator will be greater than this f naught t. If this is 0, then it is f naught t. I am adding something, that means I am increasing it here, and therefore, this is greater than f naught t, and hence V is less than c for all t. No matter how much time you apply the force, the velocity will remain less than c. And if velocities are small, that means only for small time you have applied force, that f naught square t square is small as compared to m naught square c square. In that case, yes, if this is small, if you can neglect this, then this c will cancel here, and this will be m naught f naught t by m naught, which is the classical result.